I guess so.
Go for it, Mr. Nate.
Alrighty, as Professor Hastings said, I'm going to be giving an introduction to century-scale climate anomalies. So it's been long understood that Milankovitch cycles sort of drive large-scale climate systems. And this is done in three different ways: through tilt, perihelion, and eccentricity. And so tilt is the axis that the Earth rotates on, and it varies between 22 and 25 degrees, and it alternates every 41,000 years. And so what this means is that every 41,000 years it'll go from one extreme to the other. So the northern hemisphere will be leaning closer to the sun, and then the southern hemisphere leaning closer to the sun. Next we have eccentricity, or the orbit of the Earth, and this is simply the path that the Earth takes around the sun. And we know that it's not a perfect circle, it is indeed elliptical. And on a scale of 100,000 years, this can either broaden or narrow, meaning that the Earth gets closer or farther away from the sun. And finally, we have the perihelion, which is the precession of the equinoxes. And so what this means is how close is the Earth getting to the sun in relation to orbit and tilt. And this varies on a scale of 22,000 years. And so when we have a narrow eccentricity and a strong tilt inwards, we're going to have warmer summers in the northern hemisphere. So if it leans in this way, we'll have warmer summers and warmer winters in the northern hemisphere than in the southern hemisphere, and the same can be said of the opposite. So having said that, there are two micro or century scale climate anomalies that come up: the medieval warm period and the Little Ice Age. So the medieval warm period occurs from roughly 950 AD to about 1350 AD. And then the Little Ice Age occurs from the end of that, right around 1350 or 1400 AD, all the way up until 1800, or 1850 AD, excuse me. So fairly recently in human history. And now these are proposed to have been caused by similar things. The medieval warming period was thought to have been caused by increased solar activity. So back to the Milankovitch cycles, there were either the sun or the Earth was either closer to the sun, or there were increased sunspots on the sun, increasing the radiation that was coming in. In addition to that, decreased volcanic activity. So there was less disruption of sulfur dioxide in the atmosphere. And then it is also known to have created some sort of ocean feedback system. On the opposite hand, the Little Ice Age is believed to have been caused by the opposite. So decreased solar radiation, increased volcanic activity, and some maintaining of this ocean feedback system. So we'll dive into these a little bit more. So revisiting the Milankovitch cycles, you can see that, as I mentioned earlier, they vary on tens of thousands to hundreds of thousands of years. So you can kind of see right here the cycles that they take. Large gaps with global forcing, which we have denoted in green, and temperatures, which is kind of the red and pink here. And so they follow a similar trend. And 0 right here on the graph denotes present day. And so we can see the cycle going back, and then right here we have our large increase. So we're kind of on a one thing right now. Then we have a little excerpt there at the end, and you can see that little, or pretty significant drop right there in global temperature, due to be caused by some sort of forcing other than the Milankovitch cycles. So if we take that into consideration and realize that Milankovitch cycles can account for things at tens and hundreds of thousands of years, but yet in the last 2,000 years we have this little anomaly, we have to realize that it must be due to some other forcing. So these forcings, volcanic activity to begin with. This happens when a volcano erupts, either a mass eruption or a stream, or a continual stream of mass eruptions, and sulfur dioxide is introduced to the atmosphere. Now when it is introduced to the atmosphere, it is transformed into sulfuric acid there, and then it condenses out into these sulfate particles. These, in essence, are solid particles in the atmosphere that create a blanket over the Earth. Now, if you guys think of a blanket, light can't get through. So this increases albedo, or the reflection of sunlight back into space, and decreases global surface temperatures. So with a mass eruption, it can have a pretty large effect. And then next we have some sort of ocean feedback system. Now it's believed that during the medieval warm period, temperatures reached a high enough temperatures to melt a significant amount of Arctic sea ice. And so with this melt of sea ice, there was a flux in cold fresh water coming into the ocean. Now cold fresh water is going to be less dense than the salt water that is already there. So if we look at a regular thermohaline circulation, we can see that warm water makes up the shallow current. And this is pretty influential in determining global temperatures. So if we think about it and realize that all the sea ice was coming in and it was less dense, that cold water takes over that surface current. That in turn can lower global temperatures. All right, so we have a couple different research techniques, and I'm just going to kind of go through these because some of them are a little bit tricky to understand, and they're pretty crucial to understanding how we got from measuring the ice caps and the volcanic activity, and then determining if these were the main cause, indeed the main causes of the Little Ice Age and other century-scale climate anomalies. So the first is the analysis of dead vegetation. We know from biology, or if you've taken botany already, that plants use CO2 to respirate. When they die, however, they stop this exchange of CO2 with the atmosphere. We can then use the carbon that is still present to date backwards using radiocarbon dating, which has a half-life of around 5,700 years, and date back to find when it was at that time that the plant stopped exchanging CO2. This can be possibly because that the ice sheets came over. Next is the probability density function. Now this is kind of a fun one. Has lots to do with statistics and calculus, and I'm not really good in that subject, but I'll do my best here. So probability density function is the likelihood that an event will occur in a given amount of time divided by that amount of given time. And so what they did in this experiment was they took their plant samples with the kill dates and divided them into 5-year bins, so 5-year ranges that each of them fell into. What they then did is they took up this probability density function and adjusted their calendar dates. So by doing this, hopefully they were able to create a high probability that these plants did indeed die in that 5-year range that they suspect that they did. Now it's a probability, but from what I was reading, they can get down to the tenths and hundredths of a decimal point. So it should be fairly accurate based on that. The next thing that they did was they analyzed ice and sediment cores, in particular varves. So varves are just annual laminate layers in sedimentary rock, so the layers that you see, and their thickness depends on the warmness and wetness of the summer, or the coldness or dryness of the summer. And so if you have a warm, wet summer, this in turn is going to melt the glaciers, depositing large amounts of sediment into the surrounding rock. Therefore, you're going to have a large varve. On the opposite hand, if there's a cold, dry summer, there's going to be less amount of melt happening to these glaciers and ice caps, and then you're going to have thinner varves because less sediment is then deposited. The final thing that they did was they took a computer model and proxy data. So proxy data is just archived data that's been collected from scientists, and I believe the next paper goes quite in depth about that. So it's data that other people have collected and it's just compiled. So they can enter that into a system and create a model of what global temperatures were and what climate patterns were. So what they did is using Community Climate System 3, they set up a 550-year time span and then overlaid that with known volcanic eruptions to find if there was indeed any correlation. So now that you guys have a little bit of understanding of what century-scale climate anomalies are, and we know a little bit more about the research techniques, I'll hand it over to Chris, and he'll be able to go a little bit more in depth about what this paper was really about. Thank you guys.
Or you can just use that. Oops.
I'm just restarting.
Okay, great.
Timer.
Chris is going to talk to us.
Am I good to go?
You are good to go.
Alright, so this paper is titled The Abrupt Onset of the Little Ice Age Triggered by Volcanism and Sustained by Sea Ice and Ocean Feedbacks. Introductory statement, there is no clear consensus on the timing, duration, or controlling mechanisms of the Little Ice Age. As Kenny mentioned, it's pretty known that the Milankovitch cycles and volcanism probably had something to do with the triggering of the Little Ice Age, but we do not know why it lasted for upwards of 500 years. The main objective of this study was to determine the timing and duration of the Little Ice Age, as well as the mechanism or mechanisms that sustained the Little Ice Age for several centuries. To determine these mechanisms, they use various methods, including comparison of records and proxies, analysis of C14 and dead vegetation, analysis of ice and sediment cores, and computer models. For C14 analysis, small ice caps document climate change better than, small variations in climate change better than large ice caps. So in terms of century scale climate anomalies, small ice caps are better. So the authors chose several small ice caps in Arctic Canada and Iceland, mostly on an island in Canada called Baffin Island. Baffin Island is a relatively flat landscape, and therefore the ice caps there exhibit little to no flow. So they very well preserve vegetation that was present at the time when the ice cap expanded. And the C14 activity of the plants in the ice caps can accurately date when snow line dropped below that area, killing the plants. This is known as a kill date. And these kill dates were organized into a probability density function, which Kenny explained. For varv thickness, they turned to an annually resolved record of ice cap growth from Iceland. There's a 950 square kilometer ice cap there called Longjökull, and directly adjacent to it is a glacial lake called Vitarvatn. I don't really know how to pronounce that.
Great. I had no idea that you did really well.
I looked up pronunciations, couldn't find them. But varv thickness indicates a couple of things. It can indicate annual changes in temperature on a very small scale, but on a larger scale, it can indicate variations in climate over long periods of time and also glacier power. Thicker varves are formed when glaciers do more work, if you will, on the landscape. For modeling, they did a 550-year transient experiment using Community Climate System Model 3. I do not know much about that. Major findings regarding C14 analysis. They found a cluster of kill dates between 1275 and 1300 AD after 300 years without any kill dates, more or less. This indicates that there was a period of warmth, and then around 1275, 1300 AD, there was suddenly an abrupt summer cooling. The first PDF peak coincides with 4 stratospheric sulfur loadings from volcanism, as seen in this figure. Here's where the first PDF peak is said to be around 1275, and as you can see, there's a lot of sulfur loading going on there. Second peak in composite PDF between 1430 and 1455, again, lots of sulfur loading going on here. Lack of more recent kill dates since 1455 indicates that these ice caps remained in more or less an expanded state until the past century. And a lack of kill dates between 1950 and 1250, which we now know as the medieval climate anomaly, indicates that there was either a period of warmth there or continuous cold with no new ice formation. This figure shows the composite PDF. Here's a lack of kill dates between 950 and about 1300. This was where the medieval climate anomaly was. Here's all the kill dates. First peak between 1275 and 1300, second peak around 1450, and then continuous ice cover until recent times. To resolve the issue of whether or not this lack of kill dates was due to a period of warmth or a period of cold, they turned to cores taken from Vitarvatn Glacial Lake in Iceland. And they found that increasing varf thickness correlates with the first peak in kill dates on Baffin Island. And a second abrupt increase in varf thickness in the 15th century coincides with the second peak in the PDF. Thin bars between 1950 and 1170, before the Little Ice Age began, indicate that this was, in fact, a period of ice melt rather than continuous cold. So what they found is that volcanism definitely can explain the rapid snow line lowering. However, the short residence time of atmospheric sulfate aerosols does not account for the fact that the Little Ice Age lasted for several centuries. However, their simulations showed sustained sea ice expansion following the late 13th century volcanic eruptions, and also showed sustained weakening of heat transport in the North Atlantic. Their simulation also showed an anomalously cold and fresh North Atlantic subpolar gyre, likely caused by the southward export of Arctic Ocean sea ice. And so they found that repeated explosive volcanism may have led to continuous expansion of sea ice during the Little Ice Age. Some more evidence for this: sea ice does not form around Iceland, so the appearance of sea ice around Iceland usually indicates that there's lots of ice being exported from the Arctic Ocean. The appearance of sea ice around Iceland during the 13th and 15th centuries correlates with these PDF peaks and these sulfur loadings, and yeah, it all kind of lines up. Yeah, and in conclusion, basically, as we said before, the Milankovitch cycle and volcanism are found to have triggered the Little Ice Age. However, these triggers must have engaged some positive feedback loop that kept it going and kept it going. So from their simulations, they found that these sulfur loadings and the Milankovitch cycles actually engaged a positive feedback with ocean ice that caused an expanded sea ice state in the northern hemisphere. And then lots of ice began drifting southward and generally lowered the temperature of the ocean in the northern hemisphere. And yeah, this explains why Little Ice Age lasted until past century, more or less.
Thank you.